Okay, so here we go. We just had an exam and we learned about I'm sorry, what did we learn about? We learned about, chemical reactions. We learned about gases. We learned about thermochemistry. We looked at the world from a macroscopic point of view, right? That's what we've been doing. Now, over the past couple of units, we have looked at the world at the atomic level. We came up with this really esoteric theory called quantum theory, where things at the atomic level do not behave the same way that we see things behave in our macro world. However, what we saw is that the model, although it's kind of weird and esoteric and makes some really wild predictions and descriptions, it fits, it explains the placement of the elements on the periodic table and the physical and chemical properties trends that we see amongst the elements. Now, we had live sessions up till last week, and there is a set of videos that I made that you are supposed to read on your own. I'm sorry, to see on your own, I'm sorry. There's also some notes you can download in there. So please make sure you watch those videos before you go on to the next quiz, which should be already available. Okay. I want to bring up another thing, and I gotta apologize again. It's been a rough week. I'm kind of a little stressed, and I don't know if you've noticed. I developed this thing called roseola. I had it about 2 years ago. It's just kind of like an irritation, like little zits in my nose, and it's just stress, guys. So please, I hope you don't mind my nose looking like this. But what I was gonna say is that I'm sorry, I just kind of went off the wrong place here. Let me show you on your Canvas page what your next assignment is. Of course, you just finished doing this calorimetry lab, which I haven't graded, I'm sorry. All right, I haven't finished grading it yet. There's an upcoming assignment on spectroscopy, and if you open it, it should show the instructions here. However, this is a platform that is made by a publisher who has kindly given us free access to it, all right? You need to download or read this document here that has the instructions for how to sign up. You know what? The mistake that I made was I didn't realize that the instructions, which were provided by the publisher, by the way, did not have the access code. So I put it in here. All right. So when you go back in, this is the enrollment code that they're asking you for. I'm sorry, I thought it was in the instructions handout. Okay. So basically, there's several activities in there. And again, let me show you what it looks like. Now, this is going to be my view as an instructor. It might not look the same way to you. This is a contingency course. They made it just for us to try it out, and I'm very grateful. There's a couple of things here you don't have to do. There's some things about using, lab equipment, safety, stuff like that. You don't need to do that, all right? Now, there is an activity here that also talks about glassware and math and stuff. You don't need to do that either. We've already covered that. You're going to start right here where it's going to say exploration of concentration, Beer's law, and spectrophotometry. That's the activity you're going to do. There's a handout in here. There's a video to review how to do graphs in Excel. There's talking about this concept of Beer's law. And then there's an activity you're going to do. It has several parts, and you don't need to do it all in one shot, okay? You can simply do a little bit of it and then step out. It'll keep a log of where you're at, and when you come back in, it should put you back in where you left off, okay? Now, be aware that it'll close Sunday at midnight, so please, I would start working on this, if not today, as soon as possible, because there are several activities in here. The other thing to keep in mind is that this is because it's provided by another publisher, they have their own rubric in place, and it's going to give you points and stuff like that. Just get it done. Don't worry about the points and stuff, because when I download the grades, I will adjust them, I'll prorate them to the typical score of a lab report, which was 20 points, okay? So I just want you to know that. Speaking of points, you all read my message about the exam. So like I was saying, I made a mistake in the points assigned for the questions in the test. And so I've had to go manually and go through everybody's test. So basically what will happen is I will download everybody's scores. And then what I'll do is I will have a spreadsheet where I will, calculate everything, and then I will post your grades directly to the gradebook. Okay, so that's what's going to be happening today. Okay, before we go on and get started, Alexa would like to tell us about her SI session today. What are we going to cover, Alexa?
Okay, hi guys. Our session info for the logging in is the same thing that it's been for the past 2 weeks. It's the same link, same password. And today we're covering like the conceptual meaning behind the quantum numbers, how to write the electron configurations of transition metal cations and regular cations that aren't transition metals, along with neutral atoms.
Cool. Thank you so much, Alexa, and thanks for the review sessions. Hey guys, I need to pause for a moment. I have a lot of background noise here. I'm gonna go get a pair of headsets so I can use that. So let me pause here for a moment, okay? I'll be right back. Okay, so like I said, I put on this headset because there's a lot of noise here in my community. The good thing is that, the landscape people are taking care of things and keeping everything neat, but they're doing it in the middle of the day, and there's a lot of noise here coming from from my side, my window. So let's go to our PowerPoint here that we are going to start with, and we are going to be starting a new unit here. We're going to start studying about chemical bonding. So most of the discussions we've had for the past few days have been about atoms themselves, right? And the configuration of electrons in atoms. But what about when atoms join together to make molecules or compounds? Well, we're going to spend some time today discussing what is called the Lewis theory or the Lewis model. And this goes back to a great American chemist, Gilbert Lewis. And here's the essence of the model. Let me get ready here with my markers and stuff like that. Hold on a second. Okay, here we go. So essentially, in the Lewis bonding theory, the idea is that valence electrons, and I guess you have to have watched those videos that I recorded. Valence electrons are the ones that are involved in the forming of chemical bonds. The theory also uses a structure called a Lewis or electron dot structure to represent the formation of compounds. And what is good about the theory is that it allows us to predict several properties of molecules, how stable they are, what shape they have, what size they have, and a very important property that we're going to be exploiting for the rest of the semester that is called polarity. Let's take a quick review here about valence electrons. Okay, remember that we said valence electrons are the electrons in the outer shell of the atom. These are the ones, excuse me, that are farthest away from the nucleus in those clouds of electron density that we have oscillating about the nucleus. And we found that for the representative elements, in other words, the elements in the S and the P blocks, the number of valence electrons corresponds to the group number, as long as we use the group numbering in the the U.S. or American method. So group 1A has 1 valence electron, group 2A, 2 valence electrons, et cetera, et cetera. So what we're going to do is we're going to draw little structures, little representations that to kind of like show what these things look like. So let me go over here. We're going to go to our quote unquote whiteboard, and I'm going to bring back that same table that I just showed you. Okay, here we go. So these are the elements. So how about if we take the elements in period 3? All right, let's do period 3. And we're going to take advantage of having the valence electrons in there. So let's see, we would start with sodium, magnesium, and then we would kind of jump over and have aluminum, silicon, phosphorus, sulfur, chlorine. Oops, ran out of space a little bit here. Who comes after that? Period 3. Forgot? It's argon, right? Okay. So remember, each one of these has these many valence electrons. And what we're going to do is we're going to represent each electron in the valence shell, each valence electron, as a dot. So let's say for sodium, I'm going to put a dot in there. You know, if I wanted to, I could, it doesn't have to be there. I could put it on the other side. I can put it anywhere around. It's just a representation. The symbol tells me which element it is, and the dot tells me how many electrons there are in their valence shell. Okay, magnesium is group 2A, so it had 2 dots. So again, I can put, let's say, 1 dot here and 1 dot there. Or if I want to, since the configuration is ns2, which means there's 2 electrons in an orbital, you know what? I sometimes might want to do it this way and put the 2 dots together. So it doesn't matter at this point, okay? But that's one way of doing it. Let's jump over here to aluminum. Aluminum would have 3 of these, right? So let's see, we could write it this way and just put them around like that. Or if you want, you know, you don't have to do it this way, but if you want, you can represent the configuration. 2 of them are paired and 1 of them isn't. So, you know, I could do it this way. And I can put these 2 on the top, and it doesn't really matter where I put them. Okay, silicon would have 4, so I could put 1, 2, 3, 4. Or if I want to represent what it has in here, right, ns2 and p2, well, technically, remember that the 2 electrons in the ns would be together. Let's see, this would be 3s, right? But remember when we did the configurations, when you get to the p subshell, you have multiple orbitals. So most likely 2 electrons will be in separate ones. So you can do it this way if you want. Just put them separate. I mean, I'm just trying to use the dots to give me a bit of a sense of what the electron configuration looks like, but I don't have to. Okay, phosphorus would have 5. 1, 2, 3, 4, 5. You know, that'll work. Or if I want to represent the way this looks, I have 2 of them are paired in the 3s orbital, and then 3 are in the 3p, you know, subshell. But that's 3 different orbitals, and you know, as we said, each electron is going to be in a separate one. So you know what? Maybe what I'll do is I'll represent this. I'll put 2 of them paired up, and then 3 of them kind of loose, just to represent that they are in separate orbitals. All right. Like I said, you don't have to do it that way if you want. Okay, sulfur would have 6. 1, 2, 3, 4, 5, 6. Or once more, if I want to make it look like the configuration, maybe what I'll do is I'll say, okay, I have 2 of them are paired in an s orbital, and then I have 4 in the p subshell. But that means that one of the p subshells has 2 electrons in it, so I'm going to put 2 in there. And then maybe I can leave the other 2 kind of like by themselves like that. Next comes chlorine. I would put 7, 2, 3, 4, 5, 6, 7. Or again, if I want to represent the configuration, I might have, you know, since I have, let's say, 2 in there, and then from the 5 electrons in the, you know, 3p subshell, you would have 2 of the orbitals would be, you know, have 2 pairs of electrons, and one of them would be by itself. So maybe I'll just do 1 pair for the s, 1 pair for one of the p orbitals, 1 pair for one of the p orbitals, and then that one. All right. And then argon is not in here, but since argon is a full um, shell here, it would have 8 valence electrons. And typically, one of the things we like to do, again, is represent as closely as possible. So what this is telling me is that every orbital is completely occupied. So maybe what I'll do is I'll go ahead and bypass just the 8 dots and make it like, 4 pairs of dots, signifying that every electron is paired with another electron in there. All right. So that's essentially how you do the dot structures of an atom. And you could practice some more, or alternatively, we can simply go and look at the next screen here in our PowerPoint, and that's gonna show us like the whole build out. Notice that we don't do this for transition metals, mainly because they're weird, right? We had to contend with d orbitals and stuff like that. So you can see the patterns in here. Now, one thing that you might want to ask is, what about ions? Because remember that many of these substances, many of these elements, we find them in nature as ions, right? So let's see how you would do ions. I'll just do a couple of them here. So let's come back here to our, this is the same slide that I just showed you there, right? Let's see if I can zoom in a little bit there. There you go. Whoops. There you go. So this is the same slide that you had on your PowerPoint. And what I want to do is show you how to do an ion. So for example, let's say we had chlorine, sulfur, phosphorus, right? Those are the ones that we had done earlier. And we represented them by trying to pair up electrons that we consider to be in occupying same orbitals. And again, where I put the double dot and the other ones doesn't really matter. I'm just trying to keep them organized. So remember that all of these elements are nonmetals, and so they will form ions. So if I add an electron to chlorine, I get the chloride ion, and that should have an extra electron. And remember, we said that that species now becomes isoelectronic, right, with the argon atom. Isoelectronic meaning it has the same number of electrons, but this is an ion, so we put a negative charge up there. And that's one way you can do it. Sulfur, of course, will take 2 electrons to become the sulfide ion. And I can represent that like that, but I have to make sure that I put a sign corresponding to the charge. And remember, phosphorus takes 3 electrons to become the phosphide ion, total of 8 electrons. Notice that all these electrons are being added to the valence shell, correct? And then a 3 minus here. Sometimes some authors prefer to put brackets around the dot structure just to make it distinct. Don't worry about it, okay? Now you might ask about, well, what about the metals? Well, for example, let's say that I want to do the structure for the magnesium ion. And we said that magnesium typically has the 2 electrons in the 3s subshell. And I like to put them together just to signify that they're in the same orbital. But remember that in the case of magnesium, it loses electrons, right? It loses 3 electrons. So we're going to end up with something that looks like this. Just the symbol of the element and the charge. And yeah, nothing more to it. No dots, nothing like that. So typically cations are going to end up looking just like the same way as the formula that we write for the ion without the dots. Okay, there we go. Now remember that in nature, you don't have these species sitting around or floating around by themselves. They are typically combined in the form of ionic compounds. So what we'd like to do is let's use this Lewis model to represent uh, ionic compounds. Let's go back here to our slideshow. Okay, here we go. And the question is, why do atoms bond? And I want to cover here not only ionic compounds where it makes sense, well, they're trying to neutralize charge, but what about non-ionic? What about covalent compounds? Well, what we're going to propose, again, now that we know more about energy, is that the reason chemical bonding happens is that it lowers the potential energy between the particles, right? The idea is that the chemical bond will form when the potential energy of the bonded atoms is less than the potential energy of the separate atoms. That is, the formation of a chemical bond represents a lowering of energy. Yes, it is exothermic. Yes, it generates a state that having lower energy is more stable. Now, what is it that drives that stability? Well, there's three kinds of interactions we have to consider. The nucleus of one atom repelling the nucleus of the other atom because they're both positive. You also have electron to electron repulsions because when you bring atoms together, those negatively charged electrons become a little closer to each other. And of course, there's the nucleus to electron attraction. By that I mean the electrons of atom 1 having an attraction towards the nucleus of atom 2. And so when you combine all of those, and like I've said before, we are talking here hand waving and qualitatively, but there are math functions that you can use to calculate these things per se. And these are the things that are involved in determining actually whether a chemical bond forms or not. Okay, so remember that ultimately everything has to do with energy, and there's an energy cost somewhere at some point. Now, based on just the kinds of atoms connected, we can start out by making a simple classification of bonds. When you have a metal and a non-metal, we're going to call that bond ionic, and it's going to happen by the transferring of electrons, right? The metal loses electrons, the non-metal captures them. They become respectively a positive and a negatively charged ion, and they come close together. When the atoms are non-metal and non-metal, we're going to call that a covalent bond. And in this case, the electrons are going to be shared. They're going to have a sharing, an overlap, so to speak, of the electron clouds between the two atoms. And there's a third kind, which is when you have metals linked together. We're going to call that a metallic bond. And it says here electrons pooled. We're going to discuss what that means later on. I think it's a little outside of the scope of our discussion for this unit, but we'll bring it back up again when we study the properties of solids. All right. Okay, so let's make an ionic bond. We're gonna do something we've done in the past, right? Which is forget about the path, just be concerned with where you start and where you finish. So we're gonna invent a path for the formation of an ionic compound. And in this case, we're gonna take lithium, group 1A, so 1 dot, and fluorine, group 7A, 7 dots. And we're gonna make a compound between them, and you see it right there on the bottom left. It's a salt called lithium fluoride, all right? So let's pretend we're gonna do it this way. I'm gonna start with the lithium atom, and I'm gonna say that the lithium atom is going to become a lithium ion, all right? The configuration for the lithium atom, 1s2, 2s1. Configuration for the lithium ion would be 1s2, which, as you remember, makes it isoelectronic with the noble gas helium, right? And hence the stability of forming that ion. Okay, what about the fluorine? Well, we said the fluorine would rather gain an electron to become the fluoride ion. Notice now the 8 dots are on the fluorine, but with a negative charge also. Again, fluorine has a configuration 1s2, 2s2, 2p5. The fluoride ion has one more electron. Of course, it goes into that 2p subshell. So it's 1s2, 2s2, 2p6. And as we saw last time, this makes it isoelectronic with the noble gas. That's right, neon, 10 electrons. So now in our first two steps, we have generated a lithium ion and a fluoride ion. Well, of course, since they're oppositely charged, they're going to attract each other. And we're going to bring them close together to form this lithium fluoride connection there. Notice that what's holding them together is simply the attraction of positive for negative. All right. And now let's add these three equations here, right? So the lithium ion cancels out on both sides. The electron cancels out on both sides. The fluoride ion cancels out on both sides. So I'm just adding the three equations like I've done before when I did thermochemical equations, but this is not thermochemical. This is just Lewis dot structures. And so what am I left? My final product, which is the lithium fluoride ion. So we basically kind of like invented a path for how this happens. Now, does it happen this way? You know, it doesn't matter. What matters is the product that you get at the end. All right. Now, what about nonmetals? What about when you have two atoms, both are nonmetals? So if they were to form ions, they would both want to form an anion, which means they would both want to try to get an electron away from the other one. But as we saw in our discussion of periodic trends, the ionization energy of a nonmetal is very high. They don't want to give up electrons. They want to take them. So because of this high ionization energy, it's difficult to remove electrons from nonmetal atoms. So in terms of potential energy benefit, what is better for them is for the atoms to share valence electrons, all right? And that's essentially what's going to happen here. Potential energy is going to be at its lowest when the electrons are between the nuclei. In other words, they're going to be shared. So you can see here the three diagrams in the bottom. And again, remember, these are sketches. So let's say that I have an electron, which I've put a negative sign on it, and two nuclei, each with a positive charge on it. Remember, the electron would benefit from being in interaction with both of them at the same time. Notice that in the diagram on the left, the electron is kind of like off to the side of the nuclei. And so it's not deriving the maximum benefit. It's a bit of a distance between the nucleus and the electron. And the one on the far right, you can see the electron is shifted more towards one nucleus, which is good for that, but it doesn't derive maximum benefit in its interaction with the other nucleus of the other atom. So you can see where the diagram in the middle here gives us a sketch where the electron is held right between the two atoms and therefore enjoys the maximum interaction with both positively charged nuclei. Again, remember, this is a model, okay? It's a sketch. So essentially, these two atoms are going to be sharing that electron so that that electron can benefit to the max from its interaction with both of the positive charges of those nuclei. All right? Okay, so now let's see what a covalent bond is. We say it's a chemical bond in which two or more electrons are shared by two atoms. Now, why two electrons? Well, let's consider the formation of the fluorine molecule, which is F2, right? So I bring in one fluorine atom with 7 dots and another fluorine atom with 7 dots. What would happen if these two would come together and essentially each one of them take that one lonely electron and combine it with the lonely electron of the other one and essentially hook up like this. 7 electrons there, 7 electrons here, and now they form this. Notice what happens now. If you go around each one of the atoms, counting dots, including the ones that are being shared with the other atom, we find that now that fluorine has 8 electrons around it. And if I count the one on the right, again, including the ones that are overlapping, I also get 8 electrons. This is what is called the octet rule. It's a component of Lewis' theory to propose that the reason why atoms share electrons is so that they can have a composite 8 electrons around each atom in there, including the ones that they're sharing. Notice that they're going to be shared in pairs, all right? And so what we'd like to do is use this idea of the octet rule. And again, where does that come from? Well, it comes because 8 electrons is what completes an NP, an S and P combination of subshells, right? That's the 8 electrons at the extreme of a neon or a argon or a krypton atom. The exception would be helium because it only has 2 electrons, all right? Essentially what it is we're trying to produce what looks like a full outer or valence shell. So we're going to use this to draw what we call the Lewis structure of fluorine. And the Lewis structure basically takes what we just drew here and it changes it into this, all right? Remember that in the structure, the dot structure we made, there are some electrons that are not shared. We're going to call these lone pairs, and we're going to draw them in pairs, signifying that they are paired inside one of the S or P orbitals in there. And then what we're going to do is that pair that's being shared, called the bonding pair, we're going to represent it as a line. And we're going to say that line is a single covalent bond. So a line in a Lewis structure represents one pair of electrons that's being shared, or in other words, a single covalent bond. Now, it doesn't have to be just 2 atoms. We can put multiple ones. So let's do a Lewis structure for water. So H2O. Let's bring hydrogen in with 1 electron because it's group 1A. Oxygen has how many? That's right, 6, right? Because it's group 6A. And then another hydrogen with 1 dot. The structure of water, we already know, is HOH, right? You guys know that, H2O. So let's draw it out here. Notice that in this structure, the oxygen and the hydrogens are each sharing a pair of electrons. So we're going to represent those as single lines. And now let's look at the counting of electrons around each one of these. The oxygen now has an octet around it. Now the hydrogens only have 2, but remember, hydrogen is a small atom and all it can aspire to is a complete 1s shell. But that's it, 2 electrons, just like helium would, 2 electrons there. Again, notice that in the case of water, we have 2 single covalent bonds. In other words, there's 2 sets of pairs of electrons that are shared with hydrogen. Another thing you can do is you can have what are called double bonds. This is when 2 atoms share 2 pairs of electrons. Now, later on, we'll do these things, but let's go ahead and show you what the dot structure for carbon dioxide looks like. It'll look like this. Notice that when you build this structure, the oxygen and the carbon are sharing each oxygen is sharing 2 pairs of electrons with the carbon. So each one of those would be a line, which means that now you have double lines between each oxygen and the central carbon atom. Once more, let's see if the octet rule works. Oxygen on the left, including the 4 electrons it's sharing, now has 8 electrons. Oxygen on the right also has 8 electrons. What about the carbon? Well, all of the electrons around the carbon in this model are actually shared, but there's 8 of them. Now, because the bonds here are 2 pairs of electrons each, we call them therefore a double covalent bond. We do have triple bonds also. In other words, atoms can actually share 3 pairs of electrons. Let's look at the molecule of nitrogen. 2 nitrogen atoms, each one bringing in 5 electrons. And what we're going to do here is we're going to have each nitrogen keep 1 lone pair and then share 3 pairs of electrons with the other atom. Since there's 3 pairs, each pair that is shared is 1 line. So we have 3 lines between the 2 nitrogen atoms. And notice that each nitrogen atom retains a lone pair of electrons also. Again, looking at the octet rule, including the electrons shared, nitrogen on the left has 8 total. Nitrogen on the right has 8 total. And because there are 3 pairs of electrons being shared, we have a triple bond in here. So this is essentially how we're going to, the tools that we're going to be using to cover these things. Now let's talk a little more in detail about these bonds, because right now, for example, look at the single, the double, and the triple. Now, other than the number of bonds, the picture doesn't really give us a lot of information what these are like. Are they the same? Like if an atom shares 1 pair of electrons with another one, does that look the same as if it were sharing 2, just except that it's just 2 connections? Actually, it isn't. It turns out that covalent bonds have different lengths because remember, the Lewis structure represents just the symbols of these elements. It doesn't have any information in it about the sizes of these atoms. And we saw in the recorded lecture with the periodic properties of elements that the sizes of elements are going to depend on, what is the outermost shell occupied by electrons, right? So for example, a hydrogen molecule, which has a single bond, would have a bond length of about 74 picometers. But if it's a single bond with iodine, the length of that bond is 161 picometers because iodine is a much larger atom. You can see the table here on the right. It shows you different bonds of carbon, nitrogen, and oxygen. And you can see that they're different sizes. Not only that, but there's a pattern you can see here which has to do with single, double, and triple bonds. You can see it there. And let me see if I can do this here. You can see it over here that essentially the single bond is typically longer than the double bond, which in turn is longer than the triple bond. So the trend is triple bonds are shorter than double bonds, and those are shorter than single bonds. The last thing I want to talk about in terms of bonding per se, and then we'll take a break, is the following. Are these shared electrons all the same? Remember, the model says that the electrons are kind of right in between the nuclei of the 2 bonding atoms. If that is true, then if I could map out the electron density, it should basically be fairly uniform all throughout the bond. So for example, this HI molecule, I should be able to see an electron density that's uniform pretty much across coming over from the hydrogen into the iodine with perhaps a little bit of more density right in between where that pair of electrons is being shared. What's interesting is that's not always the case. There are many covalent bonds where there is a greater electron density around one of the 2 atoms. And in that case, we have what is called a polar
covalent bond. For example, the molecule of hydrogen fluoride, HF, for which we have a Lewis structure in there, right? The structure doesn't tell me much more except how they're connected, what kind of a bond they have, and if there are any lone pairs sitting around. But here's what the structure doesn't tell me. If I were to map out the electron density, the clouds of electrons around these actual atoms, I would see something like this. I would see, and in this picture here, I don't know if you can see the colors, it looks bluish around the hydrogen and kind of pink around the fluorine. But what that means is that the area, the region around the hydrogen is electron poor, and the region around the fluorine is electron rich. In other words, it's almost like the electrons are displaced. Let's see if I can get this thing to work here. The electrons seem to be displaced more towards the fluorine atom. In other words, they're not equally shared. They are not right in the middle between the two atoms. They're displaced somewhat towards the fluorine. And because of that, what we do is we say that we have a partial charge. And what we're going to do here is we're going to use to represent the electron-rich side of that bond and the electron-poor side of that bond. We're going to use, yes, you guessed it, yet another Greek letter. This one is going to be the lowercase delta, not the triangle that we use for the capital delta, but the smaller case. Yeah, it looks like a like a head with a ponytail or something like that on top. I don't know. So we would put delta negative for the fluorine and delta positive, and what these are called are partial charges. Okay, these are not complete charges. So these are partial. Let me see if I can make this thing work. Partial charges, right? So that is what we find in these cases. Now, how would I know if I look at a molecule whether the bond that is formed between those two atoms is polar or not? Well, there it was, partial charges. I wasted time writing it out there. Sorry about that. Okay, let me just go ahead and erase that just to avoid confusing you guys. Yeah, go. Let's get that out of there. Sorry about that. I didn't realize that the slideshow itself had it in there. All right. So what determines whether a bond is polar or not is a property called electronegativity. So electronegativity is the ability of the atom to attract towards itself the electrons that are in a chemical bond. Not to be confused with the property that we talked about, electron affinity, which is a property that you measure. And it has to do with the ability of an atom to attract an outside electron to form a negatively charged ion. Electron affinities, as we said, don't have very rigid trends, but we know that chlorine has the highest electron affinity of them all. Electronegativity is not a property for which you measure units. It's built on a relative scale, and on that scale, fluorine has the highest electronegativity, all right? This is something that was developed by scientists on a scale. It's kind of like when you go like, oh, on a scale of 1 to 5, what's your favorite condiment for a hamburger? Mustard, ketchup, whatever. You scale it on a scale of 1 to 5. Well, electronegativity is a scale of 0 to 4, basically. And here is a periodic table that shows you that electronegativity has some interesting trends. You can see that essentially metals have very, very small electronegativities. Non-metals have very high electronegativities. And you can see the trends within a group. You can see where the electronegativity is lower as you go down. And within a period, it's also lower as you go from right to left. And there's fluorine with a 4.0 being the most electronegative. Remember, that value 4.0 is just a scale between 0 to 4. It doesn't have any particular physical meaning, all right? Now, in your periodic table handout that you have from the beginning of the semester, each element box has the electronegativity value in it. So you're free to use it to answer questions about this. So the way we do it is like this. This is kind of a little bit arbitrary. How do I tell if a chemical bond is polar or not? Well, I look at the electronegativity of the two atoms. I calculate the difference. And if it's a small difference, typically less than 0.4, we're going to say the bond is covalent and nonpolar. If it's somewhere between 0.4 and 2.0, and again, like I said, a lot of this is arbitrary, we're going to call that a polar covalent bond. And if it's more than 2, it's going to be ionic. Remember, in the previous approach that we had, we simply said, well, if it's a metal and a non-metal, it's ionic. If it's a non-metal, it's covalent. But now we have a bit a more nuanced type of scale, and you can see it on the next chart. So as you can see, the electronegativity difference runs in a range from 0 to above 2. And all we're saying is that somewhere in that spectrum, you have some scenarios that we're going to call ionic versus polar versus nonpolar, with the understanding that there's going to be some cases like right in between. So it's more of a continuum of bond times as opposed to a rigid, one kind, second kind, third kind, and that's it. All right. So let's go ahead and do one exercise, and then we're going to take a break. All right. I'm going to give you here 3 different compounds. A, cesium chloride. B, the bond in water, which would be the HO bond. And the nitrogen-nitrogen bond in this compound, H2NNH2, which kind of tells you the way it's written, how the molecule is built, how the atoms are connected. All right. Again, remember the trends, right? And if you look up your periodic table, you should find the numbers in there. So let's do the first one here, cesium chloride. So if you look at the periodic table, cesium has an electronegativity value of 0.7. Chlorine has a value of 3.0. So what's the difference? 3 minus 0.7, 2.3. So according to our scale that we built here, we said that if it's more than 2, it's going to be ionic, right? So therefore, this compound would be ionic. Very good. Okay, let me get you guys to do the water one. So you find H, it's 2.1. What is oxygen? 3.5. Very good. So the difference, 3.5 minus 2.1 is 1.4. So that is a large difference, but it's not 2 or more, which means that this bond between hydrogen and oxygen, therefore, is polar. Very good. It's a polar covalent bond. Okay, let's do the last one. So we're looking simply at the nitrogen-nitrogen bond in that compound. So, I mean, you probably don't have to do the calculation, but it's obvious, nitrogen is 3.0. I just want you to get practice looking up these numbers in the periodic table. So each nitrogen has a 3.0 electronegativity value. So the difference is 0, which means this is a purely nonpolar covalent bond, okay? Cool. Okay, so again, like I said, you can now do these kinds of calculations and stuff. And let's see, let's do this. Let's take a 10-minute break. We've been here for a little while. And when we come back, I'll take any questions you have, and then we're gonna talk about how do we build structures of molecules using the Lewis model here, okay? So I'm gonna pause the recording here.